Hello and welcome back. Over a number of these videos, we've sort of been covering 2,300 years of interest in Euclid's elements and people working on it, trying to prove the fifth postulate, sometimes failing in interesting ways in which, they were actually assuming something equivalent to the parallel postulate, which is pretty cool, like rectangles exist. And sometimes, failing in uninteresting ways, like just making a mistake, or sometimes failing in what they understood they were doing if they were trying to prove it by contradiction. And so they kept coming with these weird results, but they didn't get their contradiction yet. And so they thought, oh, I just wasn't able to find the contradiction, which I still believe is there. All of this interesting stuff. Over these years, there was other interesting developments as well. For example, I described the process of Euclid's elements as starting with this foundation, the solid foundation of the axioms, and then every theorem is either proved either on those or on other things that were already proven. Every step in your proof has to be either an axiom or something that's already been proven, and therefore on this sort of solid foundation, we're building bricks up one at a time in gradual layers, each solidly laying on everything that comes below it. But over the millennium, people have found some gaps in Euclid's reasoning, some things that maybe he just saw as obvious, didn't even realize he was making it as an assumption. And so they started coming up with a list. Well, here he's really actually assuming this kind of needs to be a new axiom. And so there's all of these developments over the millennium. At the end of the 19th century, so that's the 1800s, a mathematician by the name of David Hilbert was commissioned with creating a book on basically the current state of affairs in Euclidean geometry. And so he put out a book here, it's called Foundations of Geometry. And in it, he kind of showcases two things. First, he essentially comes up with a complete set of axioms. What 2,000 years, 2,300 years of finding gaps have shown us. And he ends up with about 20 axioms as opposed to the initial 5. There are so many, he breaks them into groups. There's a group of incidences and stuff. We'll look at the axioms in a minute. The second thing he showcases is this idea of creating different models to show that certain axioms are independent of the other axioms. So therefore, you really need 20. None of them you can actually prove from the others. So you don't have anything else like what happened with the fifth postulate where someone says, well, maybe Euclid's 13th axiom is really a theorem. Let's try proving that. No. He'll keep creating these models to show all these axioms are true and this one new one is false. And so it really is independent, really needs to be included as an axiom. So those are the two things he kind of showcases in his Foundations of Geometry. So let's take a look now at his axioms. What did he have here? So first of all, as I said earlier, he breaks the axioms into 5 groups. So group 1, which is axioms 1 to 8, are axioms of incidence. Incidence is the relation that a point has when it lies on a line. So if a point lies on a line, we say it's incident to that line. Or basically, if a line contains a point, we also could say it's incident to that point. Group 2, there's 4 axioms, is the axioms of order. It's essentially betweenness. Both having a point between points and possibly a ray in between 2 rays. Group 3, there's 5 axioms, are axioms of congruence, what it means when 2 line segments say are congruent to each other, or when 2 angles are congruent to each other, or maybe when 2 triangles are congruent to each other. Group 5 is a single axiom, the axiom of parallels. That's basically going to be the parallel postulate. And then group 5, there's 2 axioms, axioms of continuity. When do curves and lines actually intersect each other at a point? There's a lot of times when Euclid just made assumptions that they crossed and intersected at a point when that was not a proven or a previous axiom. And altogether, I think I counted this up right, 12, 17, 18. Yeah, it looks like there's 20 axioms. I'm not going to go through each of these 20 axioms, but let's just take a look at some of them in each group. How about that? So first of all, let's take a look at the axioms of incidence. There's 8 of them. I had to break them into 2 sets of 4. Well, come on. There we go. All right, so the first axiom, for example, is for every 2 points, A and B, there exists a line that contains each of the points, A and B. Well, this kind of sounds like the Euclid's first axiom as I articulated. But let's take a look at axiom 2. It says for any 2 points A and B, there exists no more than one line that contains each of the points A and B. Now, in Euclid, I combined those two to say, given any 2 points, there exists a unique line that contains them. And that just kind of combines the two ideas. But Hilbert breaks them out into 2 different axioms. And why? Well, one of the things is, again, you can prove these are independent of each other. Given one, you can't prove the other from it, and given the other, you can't prove the one. So Hilbert has this concern of like breaking it into the smallest pieces possible, even if you could combine them and saying there is a unique line. The smallest pieces possible because he wants to show that each piece is necessary, that you need to assume that piece. Let's take a look. So axioms of incidence, it goes about lines and planes and so on. So for example, axiom 5 says, oh, wait. What did I want here? I missed it already. So axiom 8 says there exists at least 4 points which do not lie on a plane. So axiom 8 is asserting that space is at least 3-dimensional, that the arrangement of points makes it at least 3-dimensional. So that's kind of an assertion that Euclid assumed, but never actually made as an axiom. The next group is the axioms of order about betweenness. So the first one sort of tells us that if a point B lies between points A and C, well, what does that mean? First thing is that A, B, and C must all be 3 different points on a line. And second, it says that B also lies between C and A. That means when we talk about betweenness, we don't care about the order of the endpoints. So if we say B is between A and C, that means the same thing as saying B is between C and A. And axiom 3, for example, says, of any 3 points on a line, there exists no more than one that lies between the other 2. So if B lies between A and C, you cannot also have A lying between B and C. Kind of thing which might happen is if those points were, say, on a circle. So this 3 is kind of saying our lines are not circular. And like I said, I'm not going to go through this. Now, when we're teaching our students to give presentations, we tell them that they always have to address stuff that's up on the slide. You can't just throw a bunch of stuff up on the slide, not address it, and move on. But this is a video, and you guys can all pause and read these slides at your leisure, or at least read them now while you're ignoring me talking. So I'm going to go ahead and just throw all these axioms up here, not necessarily address them all. Students, if you're watching this video, do as I say, not as I do, because reasons. All right? All right. So moving along. Axioms of congruence. So this is 1, 2, say line segments are congruent. We've got congruences for line segments and angles and triangles ultimately. Let's take a look. 2 is the shortest, at least. If a segment A prime B prime and a segment A double prime B double prime are congruent to the same segment AB, then the segment A prime B prime is also congruent to the segment A double prime B double prime. This is basically saying congruence is transitive. Apparently, Euclid forgot to make that explicit. He just assumed that. Here's some more axioms of congruence. The 5th axiom says that if for 2 triangles, their sides are congruent, then their angles must also be congruent. Now the axiom of parallels. So here's the big one. Let A be any line and capital A a point not on it. Then there is at most one line in the plane determined by line A and point A that passes through point A and does not intersect line A. Now, let me just see. It might be hard to tell with this font, but I kind of bolded the at most. That was me, to draw attention to it. Now, why don't we have to say that there is at least one? Again, people who know a little more geometry than is necessary for these lectures might be saying for themselves, well, if you don't have any parallels, you have spherical geometry. And if you have too many parallels, you have hyperbolic geometry. But that assertion that you don't have any parallels is already ruled out by other axioms, even in Euclid's original 4 other axioms. So if you're really only playing with the parallel postulate, only tweaking that and keeping everything else the same, the only other option beside Euclidean geometry is you have possibly too many parallels. You have hyperbolic. And so that's why all Hilbert has to say is that there's at most one. There's not too many. He doesn't have to assert that there's at least one. And then last but not least are the axioms of continuity. If AB and CD are, okay, let me back up. So this first one says essentially, if you have 2 line segments, then there's some number n in which n copies of the shorter line segment will exceed the longer line segment. So they can always compare the size of 2 different line segments. And the second one, axiom 2 here, basically says that, you know, everything we've done so far gets everything. It fills up the whole plane. There's no holes, no gaps. Everything is filled. Okay, so that is the 20 axioms. Again, assuming perhaps you pause the video to read some of them, of Euclid's geometry, foundations of geometry. And I said the other thing he showcased was the independence between them. So let's take a look at that real quickly. Remember those first two axioms I just went over. The first one says, given 2 points, so that was group 1, axiom 1, given 2 points, A and B, there's at least one line connecting them. Whoops. One line connecting them. And then group 1, axiom 2 was given any 2 points, A and B, there's at most one line connecting them. So what we can do here is this. Let's take a look at these two models. Here's 2 points, and let's call these two curvy things here lines. And now let's say here's 2 points without any line between them. Let's take a look at group 1, axiom 1. Given 2 points, A and B, there is at least one line connecting them. Check. Let's take a look at axiom 1, 2. Given 2 points, A and B, there is at most one line connecting them. Bah, nope, false. Let's take a look at our second model here, A and B. Given 2 points, A and B, axiom 1, there is at least one line connecting them. Nope. Axiom 1, 2, whoops, 2. Given 2 points, A and B, there's at most one line connecting them. Bing, check. So what these two models prove is that axioms from group 1, 1 and 2 are independent of each other. You cannot prove the second from the first. And so this proves you cannot prove the second from the first. And this proves you cannot prove the first from the second. So they really are independent, really need to be different axioms there, both included. You can't have something like the whole thing with Euclid where, oh, maybe you could prove this second axiom from the first one. You don't need to include it as a second axiom. Yes, you really do. But this is sort of the second kind of thing he showcased in his Foundations of Geometry. All right. Now, in a way, this book, Hilbert's Foundations of Geometry, was sort of the capstone of mathematicians' interest in Euclid's elements. Not in mathematicians' interest in Euclidean geometry, but at least the book that Euclid put out in 300 BC on the elements. So for 2,300 years, mathematicians have been looking at it and finding new axioms and trying to prove the fifth postulate and all of that stuff. And this book was sort of a nice bow on all of the work for those 2,300 years. Mathematicians will continue being interested in Euclidean geometry, but not necessarily in Euclid's elements per se anymore. One of the reasons is in the 20th century, mathematicians develop a whole bunch of new fun toys to play with, like topology and algebraic geometry, sheaves and kernels and all sorts of stuff like that they have a lot more fun with, and which is completely goes beyond the actual Euclid elements. Another thing is their interest sort of brought in. A theorem in the 20th century in Euclidean geometry might sound something like this. Such and such is true for n-dimensional Euclidean geometry for all n greater than or equal to 7. Imagine grabbing Euclid out of 300 BC and plopping him in the 20th century and giving him that theorem. What the hell are you talking about? In my last video, I talked about if you took someone from 1850 and put them in 1950 and they looked at mathematicians' works on, like fields or modules or something, they'd say that's not mathematics. This is like a million times more if you had taken Euclid out and then dropped them in the 20th century and looked at these sets of concerns. So mathematicians grew into a new set of toys to play with, a new set of interests they had beyond what was contained in Euclid's elements itself. Now, like I said, this stuff still maybe looks at Euclidean geometry, but n-dimensional Euclidean geometry or all sorts of aspects that Euclid never even really dreamed up of. So now, so this really was the mark of the end of this sort of millennial-old work on Euclid's elements. And notice that it's also with this whole independence of the axioms thing, ushers in the beginning of this new way I talked about thinking about mathematics, that it's not about points or lines or something, but about whether the statements imply each other or not. And so we can say that T is a theorem of the axiom set A would mean that any interpretation that makes the axioms A true will also make the theorem T true. And some of the strength of mathematics is we don't assert what it is those axioms A are really talking about, because they could be talking about infinitely many different things, and each of those things they could be talking about, the theorem would also be true about that thing. I put it the following way, that one proof could actually give us infinitely many truths. And that all depends upon our ability to reinterpret the words in what we're talking about in our axioms. By line, we could mean this, we could mean that. By point, we could mean this, we could mean that. And so we have this whole reinterpretability in mathematics. Not all mathematicians bought into that. There's definitely a period of conflict in there. One of the mathematicians that really had a problem with this new way of doing things was a complex analyst by the name of Gottlob Frege, a German at the University of Jena. And God, I produced Gottlob Frege correctly, and I mispronounced Jena. Anyway, Frege started writing a correspondence to Hilbert. And at this time, believe me, Hilbert was way well-known, very popular. Frege was kind of unknown. And Hilbert, to his credit, graciously wrote back, and they went back and forth for a while. Neither seemed to be able to convince the other of their side of things. And eventually, I think Hilbert just sort of gave up on humoring this no one that he had never heard of before. And that was about the end of that. So what was their debate about? What I'm going to say is not necessarily how they articulated it in their letters, because I think they're both still working this out, talking it out, if you will, and struggling, but how people after them kind of distilled the core of the debate between them. And the idea of the debate between them was this: what sorts of things logically imply each other? What things carry logical relationships? Is it the actual words, the sounds I'm making when I'm speaking, just the symbols on the paper? Or is it actually the thought behind the words I'm speaking or the symbols I'm writing on the paper? Because if you could determine the logical relation between statements by willy-nilly reinterpreting what the words mean, that means those logical relationships must be between just the written words on the paper and not about what they mean. So does that sound reasonable to you? Is A logically implies B a statement about what you've scribbled on the paper, the things you've scribbled on the paper, or is it about the thoughts you're thinking when you express the statement A or the statement B? Frege thought logical relations held between thoughts, and therefore we are not allowed to just reinterpret words willy-nilly. Or if we did, we would be talking about different things. If we reinterpreted our words, then we're talking about different thoughts, and it's going to tell us nothing about the logical relationship between the original thoughts. So for example, take the Beltrami-Klein model of the circle with the chords between it. That doesn't prove anything about whether the fifth postulate of Euclid's axioms, which are talking about lines, real lines, is dependent or independent of the previous ones, because the Beltrami-Klein model is about chords. And so it doesn't really say anything about the logical relationship between our thoughts about real lines and real points. Now, Hilbert, on the other hand, really bought into this whole like Beltrami-Klein shows you can't prove Euclid's parallel postulate from the previous four axioms. And this example I gave you about his first two axioms being independent of each other, that just assuming there is a line connecting any two points doesn't necessarily imply it's unique, and implying that there's at most one line doesn't necessarily imply there exists a line, back and forth. He thought that was all great, but that does seem to imply that logical relationships are not between what we're thinking about or what we mean by the words, but logical relationships are just between what's scribbled on a paper or the sounds we make by our voice. And that logical reasoning is just a action of symbolically, mechanically manipulating those symbols on the paper without necessarily having a thought process of understanding what it is we're doing. That logical reasoning is really a mechanical process amongst meaningless words. And he bit the bullet and he said, sure, yeah. Now I'm going to go deeper into both Frege and Hilbert's perspectives. I'm going to talk about Frege in my 17th lecture, and I'm going to talk about Hilbert in my 18th lecture. But first of all, to clear up a little misconception, some people have taken this to mean that Hilbert thought that all of mathematics was meaningless and that it was all just empty symbols and stuff, and that is not the case. He may have argued that our logical reasoning is a mechanical process independent of the meaning of the symbols, but he definitely thought math had meaning. He wrote a whole much lesser known book called Geometry in the Imagination with Cohen Voss, I think, as a co-author. So he did believe it was meaningful. He just believed that logical reasoning didn't depend upon the meanings of the words. And I'll get into that. Like I said, 17th video, going to be more about Frege, 18th video, more about Hilbert. So, who was right? Well, ask yourself that. But we could ask another question. Who won out in the end? Who did history finally agree with? And the answer to that is essentially, in a way, they both won. Let's go back a second. Mid-1800s, there's this thing that I've been teasing all along. I will get to it in the next video, which I'm calling the collapse of the calculus. Essentially, it was the final problems and collapse of the infinitesimal calculus. Mathematicians and philosophers kind of underwent a shotgun wedding in which the mathematicians were scrambling to somehow rebuild a foundation for calculus in which it would finally work. And that led to a sort of a nice long period of really good work between mathematicians and philosophers where cutting edge mathematics and cutting edge philosophy were all tied up in one bow. And we could see this Hilbert-Frege debate as being an example of like the pinnacle of real mathematicians with real philosophical concerns and it all being well informed by each other. Well, as of maybe say the 30s or so, 1930s or so, mathematicians and philosophers kind of ended up going their own ways. The shotgun wedding didn't really last more than several decades. And in the divorce, the mathematicians got Hilbert and the philosophers got Frege. So in the long run, the mathematicians thought Hilbert was right, and they continue having no problems showing dependence or independence of axioms by creating these models. And the philosophers took Frege, and they thought, no. Well, like I've said before, philosophers rarely agree on anything. But let's just say in the Hilbert-Frege debate, they went with Frege. So that, like I said, is going to be my 17th lecture is going to be on Frege. My 18th lecture is going to be more on Hilbert. Yeah. But the next lecture, I'm finally going to get to this collapse of calculus. Why did we go from the infinitesimals to the limit system that I've been teasing all along? And that's really going to create some chaos and people scrambling to try to fix things. And that's a great point in the history of mathematics, really fun. And then the lecture after that is going to be how the solution mathematicians came up with, the theory of limits, led to a transfinite arithmetic and set theory as we know it in the 20th century, which kind of leads to a new foundations of mathematics. We've gone and asked all along, what is mathematics about? That's sort of one of the themes of this lecture series. And originally we said all is number, and then we said, oh no, that doesn't work. So everything's based on geometry. And then Kant came along and said, oh, everything is intuition and manifolds in the mind. And now in the 20th century, mathematicians are going to start saying it's all set theory. And that's going to develop out of the theory of limits, which is the fix to this collapse in calculus, which I'm going to talk about in the next lecture. And I look forward to seeing you there.